Okay guys, so in the last video we have learned how to calculate the shear stress due to bending moment. Okay, so recap one by one. Initially we had a beam like this one and it was subjected to a loading like this. Okay, symmetric, and the middle part or this one was in a pure bending condition. Okay, and we have calculated the bending stress, okay, for this middle part, and we consider during the derivation of the formula that any plane section remain plane, okay, or you can say that we neglected the shear deformation. Okay, and in this video I will again discuss that actually this plane section does not remain plane when this particular part is not in pure bending. Okay, and for that, you know that in the last video we have discussed that when there is a beam like this one which is subjected to any arbitrary loading like this, it has a bending moment diagram like this. Okay, and any part of this beam is under the action of bending in association with some shear force. Okay, and due to this variable bending moment at two different cross section, we have calculated the shear stress due to bending. And if you can recall, you know that is tau is equal to VQ by IB. Okay, so till now this is our progress. Okay, so the mission of this video is to say that to prove that actually this plane section does not remain plane. Okay, or you can say that shear deformation actually exists in practical cases when any two particular part of the beam under the action of variable bending moment. Okay, so let's start with this formula. In the last video we have only derived this formula, we have not applied anything. Okay, so first applied this one on any rectangular cross section. Okay, so let's say this is our beam and it is under the action of this load. So the shear force diagram is something like this one, correct, and the bending moment diagram is like this one. So if we consider any two different cross section at the left side, you know there is shear force, okay, and variable bending moment. So this part is under the action of shear stress 2 in association with your bending stress. Okay, and what is the shear stress? Shear stress can be written as tau is equal to VQ by IB. Okay, now let's say the cross section of this beam is a rectangular cross section. Okay, so rectangular cross section with, let's say, height is h, standard height is h and width is b. Okay, and it has a neutral axis at a depth of course h by 2. So the depth of neutral axis is h by 2. So this is the cross-sectional property of this rectangular cross section, and our job is now to find the actual equation of shear stress at any height of this section. Okay, so just clean everything. Okay, and we will again draw this rectangular cross section here. So let's say this is the width b and this is the height. Okay, what is the neutral axis? It is situated at a depth of h by 2. Okay, so this is h by 2. Our task is to find what is tau at any depth. So at any depth means, let's say we are considering at a depth of y. Okay, we are considering the shear stress at a depth of y from the neutral axis, and here we have considered a very small, very infinitesimal area, that is known as dA, and here dA is nothing but, you can say that width, that is b, times dy. Okay, this thickness is dy. Agree? So this is coming as b times dy. This is the cross section, and you know that if in this cross section where we have considered this rectangular section, let's say here shear force is constant. Okay, and we can calculate this from this shear force diagram. Let's say this is b, and also for a rectangular section, this I, so v is constant. Okay, and this I is also constant, that is given as simply b h cube by 12, nothing new. Okay, and also here you can see that b is also constant. So here b is constant, v is constant, and also I is constant. So what is q actually? What is q? So q is the statical moment of the area, okay, above which we are considering the shear stress. So we are considering the shear stress at this level. So the whole area below this one, that means this one, is contributing to the shear stress at this level. Any confusion? We are considering the shear stress at this level at a distance of y from the neutral axis. So the whole area at the bottom of this level is considering to this shear stress. Now we have to calculate q for this particular portion. Okay, now what is the formula for q? What is the formula for q? Q is the integration of the moment of very small area. So we have considered this dA. Okay, this is the dA. What is the moment of this dA about this neutral axis? Simply y times dA, because it is situating at a distance of y from the neutral axis. Got it? And we have to integrate it from this level to this level. Okay, because the whole portion is contributing. Okay, let me mark this contributing area. Okay, so this is the contributing area. Got it? So the integration limit is coming as from, let's say, y to this one. What is this distance? Simply h by 2. Okay, so y to h by 2. Got it? Now put the values y to h by 2, y times dA is coming as b dy, b times dy, or you can say b is constant, so simply integrate y times dy from y to your h by 2. Okay, and this gives us b by 2 times y square. Okay, with limit from y to h by 2. So this gives us b by 2 times h square by 4 minus y square. So this is cube. Okay, so we are getting actually tau. Okay, let me use some different color. So tau is actually coming as v is constant, I is constant, b is constant. Okay, so only variable thing is your q. Okay, so q is coming as b by 2 times h square by 4 minus y square. So this is the formula for shear stress at any depth y from neutral axis for a rectangular section. Okay, now let's try to put the values, or let's try to draw this shear stress distribution for your rectangular section. Okay, so if we simply try to draw this shear stress distribution, you can see that if this is the neutral axis, okay, then at a distance of h by 2, when y is h by 2, it is coming something here at the free surface or at the edges of this rectangular section. So what is the value there? Okay, we are considering the height by this line, okay, and we are plotting the values by this color, okay. So at y is equal to h by 2, you can see that tau is something, it is coming as 0, okay. So here at this point it is 0. Similarly here it is 0 from symmetry, okay, and at the center or at neutral axis y is 0. So tau is coming as simply v b h square divided by I times b times 8, okay. So here you can see the value is something positive, so here it is value. And now from 0 to this neutral axis, how it varies? It varies linearly? No. Here you can see that tau is a function of y square, so simply it varies parabolically, okay. So the distribution looks like this, okay. So maximum, this is the maximum shear stress, and it is equals with v b h square, cancel b and b, so we are getting simply v times h square divided by 8 times I, okay. Now also if we simply again simplify this formula, we can replace I with our formula, that is bhq by 12, okay. So we are getting, replace simply I, so we are getting tau max as v h square divided by 8 times I is b h cube divided by 12, or we can say this is 4 2 and this is 3, so 3 by 2 times v, and cancel h square with h cube, we have only v divided by bh, and bh is nothing but the area of this section. B is the width, h is the height, okay. So finally we have tau max as 3 by 2 times b divided by a, okay. That is the average shear stress. Average shear stress is mean shear force divided by the cross sectional area, that is average shear stress, okay. So here you can see that at the neutral axis we have a maximum shear stress that is almost 50% higher than the average shear stress, okay. So again let me clear all these things, we don't need those things right now, okay. So just like this rectangular section, you can also find the shear stress distribution for a circular section like this, just like this one. It also varies parabolically, you can prove it, okay. Or if you consider a triangular section like this, okay, let's say you have a triangular section like this one, which have a neutral axis somewhere here. Here also the distribution looks like this, the maximum of course here at this neutral axis, okay. This is the tau max. Now if you consider a diamond shape, okay, let's say you have a diamond shape like this, okay. So here you can see the distribution just like triangle, maximum at this point, maximum at this point, but it is not 0 here, it is not 0 here, because at this point in case of a triangle it is a free surface, okay. So that is why the stress was 0, but here it is not free surface, that is why here there is some shear stress, okay. Now one thing you can see here that for every cross section there is a variation of stress. Okay, agree? So if we consider for this, for example, just consider this rectangular one. Here you can see that the shear stress is 0 here and maximum at neutral axis. Okay, so if we consider this rectangular cross section again, this is valid for all these things, for all the cross section. Okay, so don't worry, in the next video I will discuss about your I section. Okay, how shear stress is distributed in I section I will discuss there. Okay, so for this cross section, here you can see that here shear stress is simply 0 and here it is maximum, just like that. Here it is 0 and here it is maximum and varies like this. Okay, now go back to your first class of strength of material, where I have told you that stress is proportional with your strength. Okay, so if stress is 0, simply strain is also 0, and stress is maximum means strain is also maximum. Got it? So where you can see strain is 0. How? I will tell you. Here strain is maximum. Now for a shear strain, it is not a displacement like this one. It is not a displacement like this, that you are applying some shear force like this and you have some displacement. This is not gamma. This is not true. For this one, the strain is an angle. Okay, so if you have shear stress like this, it has deformed, so this is the strain actually, gamma. That means at this point gamma is 0. Okay, let's try to visualize that. Okay, so let's say you have a beam, a cantilever beam like this. Okay, this is the cantilever beam. Okay, and this is the height of the section and this is the length. Got it? Now let's say you are applying a load here. You are applying a load here. This is the applied load P. So of course in between there is both, in between the support and the load there is both shear force and bending moment. So initially, if you, let's say this was your neutral axis. Okay, so initially let's say you have drawn a plane. This is the plane. Okay, so as for our assumption that plane section remain plane, based on this assumption we have derived the equation of stress due to bending moment. Got it? M by Z. But here you can see that strain, shear strain, of course, shear strain at this edge is 0. That means it remains same, no deformation at this point. The angle is 0, but here there is some value of angle. So the angle here at this neutral axis is this one. Okay, it is only possible if your plane bend like this. Okay, if this is the bend, only in that case it is possible. Thus at this point, at the edges, the strain is 0. Here you can see that the slope is 0, so strain is 0. But at neutral axis the slope is maximum, so gamma is maximum. Sorry, your stress is also maximum. So the all the vertical plane which you have drawn at the face of this beam now become this one. Okay, so plane section don't remain plane when your beam is not subjected to pure bending. Okay, so that's it.